Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to this channel Chandan Physics. In this video, we are going to discuss first and second order phase transitions with examples. Let's begin. What is first order phase transition? The phase changes from one state of matter to another, like the transition from solid state to liquid, or liquid state to vapor state, or from solid state to vapor state. These are known as the first order phase transition. Transitions of phase. The examples like solid to liquid, liquid to vapor, or solid to vapor are under the category of first order phase transitions. Here, what happened in case of first order phase transitions? There is always the absorption or the emission of a certain amount of heat. That heat is known as the latent heat per unit mass when the first order of phase transition is taken into considerations. Here, entropy and volume of the system changes abruptly. Entropy and volume of that particular system changes abruptly, and here the absorption or the emission of certain amount of heat, which is known as latent heat per unit mass, that happened in case of first order phase transitions. Latent heat per unit mass, entropy, volume of that of system changes. This occur in case of first order phase transitions. Now, just it opposite means the phase transitions in which no latent heat is involved nor entropy and volume of the system changes are called the second order phase transitions. No latent heat is involved nor entropy and volume of that of system don't change. These phase transitions are known as second order phase transitions. Some examples of second order phase transitions: transition of a superconducting medium to an ordinary conductor, and another example, transition of a ferromagnetic material to a paramagnetic material at Curie temperature. These two are the example of second order phase transitions. These are some basic points regarding first order phase transitions and second order phase transitions with examples. Now, we mathematically show how these phase transitions are occurred. To show mathematically, in a first order, the change takes place at a fixed value of temperature and pressure. What happened in first order? In first order, the change takes place at the fixed value of temperature and pressure. That means the change in temperature will be 0 and change in volume will be pressure, that is change in pressure will be 0. The changes occurred in case of that of first order phase transitions. So that process means temperature is 0, change in temperature 0, change in pressure 0. Change in temperature means here temperature is constant, that means it will be the isothermal process, and pressure is constant, means the change in pressure will be 0. That thermodynamic process is known as isobaric process. So, combining these process, that process is known as isothermal isobaric process. Isothermal isobaric process. Isothermal means temperature constant, isobaric in the sense pressure constant. Now, according to Maxwell's thermodynamic relation, Maxwell's thermodynamic relation dg, g with the Gibbs free energy, is equal to minus s dt plus v dp. So dg, g is a function of temperature and pressure, and the Gibbs free energy is the function of temperature and pressure. Hence, since we consider isothermal isobaric process, temperature and pressure remains constant, so dg will be 0 here as we take isothermal isobaric process. Thus the Gibbs potential G is a function of what? Temperature and pressure. Therefore, right here, that is G is a function of temperature and pressure. Therefore, del G by del T at constant pressure, that term will be 0. So dg is equal to minus s dt. So dg by dt at constant pressure will be minus s, and at constant temperature that term will be 0, that term exists. So del G del P at constant temperature, that will be V. These are equation I, equation II. Now, let us suppose that a system, we consider a system here. Suppose a system let us suppose that a system consists of substances which contains two phases, means phase 1, let phase 1 and another be phase 2. Let mass of the substance in phase 1, mass of the substance in that of phase 1 will be m1, and mass of the substance at phase 2, let m2, and these two state of that of equilibrium. Now let G1 with the Gibbs function, that is the Gibbs function per unit mass at phase 1, and G2 be the Gibbs function per unit mass for phase 2. These two are in equilibrium, state. So what happened here? The Gibbs function of that of entire system, here the Gibbs function of entire system becomes, that is G, the Gibbs function of that of entire system, that is m1 g1 plus m2 g2. Here g1 and g2 are constants. Then we differentiate. Here g1 and g2 are constants, which is known as the Gibbs function for unit mass. Now differentiating, what we have, dg is equal to dm1 g1 plus dm2 g2. g1 g2 are constants. Now for an infinitesimal phase change, the changes in m1 and changes in m2 are very small, that we can say for infinitesimal change what happened, for infinitesimal change dm1 plus dm2 is equal to 0, and ultimately dg is equal to 0 and dg is equal to 0. Why? The changes in m1 and m2 means the changes in mass m1 and m2 are very small, in case of what? In case of infinitesimal change. So that equation change to, that equation will be 0. So dm1 g1 plus dm2 g2, here g1 g2 is equal to 0, or dm1 g1 minus dm1 g2 is equal to 0. Look that dm1 g1 plus dm2 g2 is equal to 0, that means dm1 g1 is equal to minus of dm2 g2. So in place of dm2 g2 I can substitute dm1 g2, or dm1 taking as common, that is g1 minus g2, which is equal to 0, or g1 minus g2 is equal to 0, or g1 is equal to g2. That is equation number 3. Here I write here that term indicates, although d m1 g1 is equal to minus d m2 g2 for that equation. Therefore I substitute that one. Now what that particular equation implies? It implies that Gibbs function per unit mass has the same value for that of two phases. So I write here, it implies that Gibbs function per unit mass has same value for the two phases, Now let us consider the temperature at which the phase transition takes place is dependent on the pressure. So the temperature is depend upon that of pressure. The temperature T What is that of temperature at which the phase transition takes place is independent, sorry, that is dependent, is dependent, that depend upon pressure, that is dependent on the pressure P, on the pressure P. So, if there is a change in the pressure, ultimately there will be the change in the temperature. If there is a change in pressure, there is a change in pressure, from, let change in pressure, that is P to P plus dP, that is the change in pressure. As a result, then two phases will come to equilibrium at temperature T plus dt. Change in pressure indicates to that of change in temperature, and so that the changed value in phase function, the changed value of G1 and G2 will be G1 change, that is G1 plus dG1, change in G2, that is G2 plus dG2. What I say, temperature depended upon pressure, so change in pressure at equilibrium enhance to that of change in temperature, that also change the value of G1 and G2. Change in G1, that is G1 plus dG1, and change in G2, that is G2 plus dG2. What happens in case of equilibrium? Therefore, for equilibrium G1 plus dG1 is same as G2 plus dG2. These two are same at equilibrium condition. As you know, G1 is same as G2, therefore dG1 is same as dG2. As we say, G1 is equal to G2. Now, G is a function of temperature and pressure. As G is a function of temperature and pressure, so I write, therefore dG1 is equal to del G1 by del T at constant pressure dt plus del G1 by del P at constant temperature dP. Let I take, that is equation number 4. That is equation number 4. And for second one, and for dG2, it will be del G2 by del T and constant pressure dt plus del G2 by del P at constant temperature dP. Let be. Now, putting the value of dG1 and dG2 in that of equation number what? In the equation number that equation, dg1 is equal to dg2. So just we put the value, therefore we write these two are equal. So these two equations are equal. So I write del g1 by del t at constant pressure dt plus del g1 del p at constant temperature dp is same as that, that is del g2 by del t at constant pressure dt plus del g2 by del p at constant temperature dp. Let equation number Vi. Now we know that del g1 by del t at constant pressure will be what? Look at that equation. Del g by del t at constant pressure, that is minus s, and del g by del p at constant temperature, that is V. So here I implement that will be minus S1, and again at pressure del G1 by del P at constant temperature, that is V1, and dg2 by dt del G2 by del T at constant pressure, it will be minus S2, and here del G2 by dP del G2 by del P at constant temperature will be V2. Now putting these values in equation Vi, what we have here, the terms like S1, S2, V1, V2. S1 and S2 are the entropies per unit mass of that of substance in phase 1. Here S1 and S2, just write here S1 and S2, just S1 and S2 are the entropies per unit mass of the substance in phase 1 and phase 2, phase 1 and phase 2, phase 1 for S1 and phase 2 for S2. Again V1 and V2 are the volumes per unit mass, are the volumes per unit mass of substance in phase 1 and phase 2, phase 1 and phase 2 respectively. Means phase 1 is the V1, phase 2 for V2, here phase 1 S1 and phase 2 for S2. Now putting these values in equation number Vi, what happened? Putting these values in equation Vi, we get that will be minus S1 dt. So that equation changes to minus S1 dt plus V1 dP is equal to minus S2 dt plus V2 dP, equating dt and dP. dt as common, so S2 minus S1 to that side, here dP taking as common, that is V2 minus V1 on that side. So, dt by dp, so dp by dt, here dp by dt, that will be S2 minus S1 divided by V2 minus V1. Let equation number V double I. Now, take the latent heat L. Now, the latent heat L is the amount of heat per unit mass, is the amount of heat per unit mass given to that of system or extracted from it, is given to that of system, or we can say extracted, or extracted from it during the small changes in the phase, small changes in the phase. What happened here? That is, L is defined as T S2 minus S1 and change in its entropies. As we know, dq is equal to T ds, and that dq is nothing to that of L and the latent heat. So, L will be T into S2 minus S1. So, that S2 minus S is that S2 minus S1 is equal to L by T. Now, putting that a value of equation, therefore equation V double I becomes dp by dt is equal to L divided by T V2 minus V1, and the required expression. This is the general equation, that is the general equation governing a first order phase transition, governing a first order phase transition. Now, using the equation of first order phase transition, we can show how the curves are found in case of that first order phase transitions, means how phase transitions are occurred. Taking an example to show it, here when we apply this equation to equilibrium between the liquid and gaseous phase, example apply this to equilibrium between liquid and gaseous phases, liquid and gaseous phases. What happened? Liquid and gaseous phases. The equation becomes the famous Clapeyron's latent heat equation, and that derives on the basis of Maxwell's relations. So, the equation was dp by dt L V2 minus V1. So, I write that equation becomes Clapeyron's latent heat equation. Clapeyron's latent heat equation. We studied the Clapeyron's equation in upcoming videos. So, just remember that Clapeyron's latent heat equation, it is dP by dt at saturation is equal to L2 divided by T2 Vg minus V1, whereas Vg and not V1, that is VL. Vg and VL are the volume per unit mass of the substance in gaseous state. So, we write here what is Vg and VL. Here Vg is the volume per unit mass of the substance in gaseous state. Similarly, VL is the volume per unit mass of the substance in liquid state. And the transition temperature be T2 be the transition temperature, and L2 is the latent heat of vaporization. L2 is known as latent heat of vaporization. What is latent heat of vaporization? That is defined as the heat required, to convert a unit mass of liquid into gaseous phase. To convert a unit mass of liquid to gaseous phase. This is the latent heat of vaporization, heat required to convert unit mass of liquid to gaseous phase, latent heat of vaporization. Again, similarly, we call the amount of heat required to convert a unit mass of solid into a liquid phase. Similarly, heat required to convert a unit mass of solid into a liquid phase, as known as latent heat of fusion. That is L1 here. Heat required to convert a unit mass of solid into a liquid phase, which is known as the latent heat of fusion. Here is the latent heat of vaporization, and the equation will be, that is dP by dt at saturation will be how much? That is L1 divided by T1, that is VL minus Vs. Similarly, VL is the volume per unit mass of the substance at liquid. Here S is the volume per unit mass at solid, of solid. Again, if the transition takes place, again this is the equation here, gas to liquid. Here again transition takes place from solid to gaseous phase. Transition takes place from solid to gaseous phase. The latent heat is known as latent heat of sublimation. Latent heat of sublimation. Transition takes place from solid to gaseous. The latent heat is known as latent heat of sublimation, and that is given like this: sublimation L3, that is dP by dt at saturation is equal to L3 divided by T3 Vg minus Vs. Let the above three equations, this, that and that equation, let we represent the graphical view, and the equations are show the slopes of the curves of the respective graphs. Let me take the graph here, graphical view. If we take temperature on x axis and pressure on y axis, then what happened? That graph shows, graph will be this. A, B, C. Here is the liquid, here is the gas, here is the solid, and that curve is vaporization curve, and that curve is the fusion curve, and that curve is the sublimation curve. So, what we conclude from that of particular graph, if here that the graph, from graph if G of solid is equal to G of liquid, that indicates the curve OC. And represents the phenomenon of fusion, that indicates the phenomenon of fusion. and here if G of liquid is equal to G of gas, G of liquid is equal to G of gas, that represents the curve OB, which is the phenomenon of vaporization, that represents the phenomenon of vaporization. And again, when G of gas is same as G of solid, then that represents the curve OA, which is the phenomenon of sublimation, that is the phenomenon of sublimation. But at O point, three curves are met, and that point is known as triple point, that is the triple point. O point is known as the triple point. What happened in that of triple point? In that of triple point, here G solid same as G liquid is same as G of gas. All these are same at that of triple point, that is the case of equilibrium. So these are some conclusions that are drawn from the corresponding graph. So what we have studied throughout that of video lecture? So here we studied about the first and second order phase transitions with examples. These are the basics definitions of first and second order phase transitions with some examples. Now we mathematically show, taking the isothermal and isobaric process and applying the Maxwell's thermodynamic relation here. Then proceed mathematically, taking the system having two phases at equilibrium conditions. Then you apply the mathematical relations here. After taking these mathematical relations, we get an equation, that is dp by dt is equal to L divided by T whole into V2 minus V1, which is the general equation governing a first order phase transition. And using that general equation, we take an example to apply that equation to the equilibrium between liquid and gaseous phase. That equation changes to Clapeyron's latent heat equation, and these are the parameters, what is Vg, Vl, T2 and L2, which is known as the process of latent heat of vaporization, latent heat of fusion and latent heat of sublimation. These three phenomena are shown in that of particular graph, and what happened in that of graph, we consider particular phenomenon and the corresponding mathematical relation. So with this useful and informative notes, let me wind up this session. Thank you.